Well, hello, friends. It's MoNaCo here, getting close to the end of our bonding unit notes. We're on our ninth video. We're going to look at polar versus nonpolar compounds today, and we're going to be able to tell the difference between them by looking at a couple things. One, molecular symmetry, and two, differences in electronegativity between the elements that are covalently bonded together. Polar and nonpolar compounds are only for covalent type compounds. Okay, so what are the major differences between polar and nonpolar compounds? Well, first of all, symmetry. Okay, symmetry has everything to do with polarity. And I think of polarity like how the Earth has a north and south pole. They're two opposite ends. Well, if I apply that to molecules, then I have to think about it, well, a molecule that has opposite ends. Now, every molecule has an opposite end. It's just a question of, does that element on that one particular end of the molecule pull the electrons towards itself more than the other? Because then we have a situation where there's a push me pull you for the electrons over the chemical bond, and one of the elements having a higher electronegativity is going to win that pull, which would lead the molecule to have two opposite ends. Now that usually happens when you have an asymmetrical molecule. A molecule that's perfectly symmetrical, like hydrogen, HH, neither of these elements pull the electrons to one side more than the other. So this would be a nonpolar molecule because it's perfectly symmetrical. You can't cut it any way that makes it lopsided. Okay, so that's one thing to keep in the back of your head. The second thing is, if the symmetry test fails, then you have to go to your table S and reference tables and periodic tables so that you can find the differences in the electronegativity and compare them and do it the hard way with the mathematics. But the easy way to do these is to look at molecular symmetry. So let's get into our notes here today. So first of all, a covalently bonded substance always has two or more nonmetals together. Okay, they're bonded together. And molecular compound is what we call a covalent compound. So that's a synonym. Molecular, covalent. That's what we mean when we say a covalent compound. It's a molecule. Two or more nonmetals sharing electrons in order to make that happen. Okay, so polar molecules are asymmetrical. Okay, they do not have symmetry. That results from the uneven or unequal sharing of electrons. It doesn't pass the mirror test, and it can't be folded onto itself to reflect. So two atoms with different elements or different electronegativities, that's usually the situation that we're running into. Also, if you have more than two atoms, we get unbonded electrons, or lone pairs that we like to call them, around the usually most central or most electronegative element in playing the game. So for example, in hydrogen chloride, HCl, let's draw that molecule, HCl. Well, hydrogen would be on the left-hand side. Chlorine would be on the right-hand side. After these have been covalently bonded together, there's a covalent bond in the middle, and chlorine has 6 lone pairs of electrons. So I want you to label up those 1, 2, 3 lone pairs of electrons. Now, if we're looking at this molecule to decide, do we have symmetry? Does it pass the mirror test? You might want to look at it in two different ways. Along the x-axis, like this, you look above and below and you say, yeah, it's symmetrical. Great. But if you cut it along the y-axis here, down the middle of the covalent bond, you see one side's hydrogen, the other side's chlorine. And furthermore, chlorine, with those 3 lone pairs of electrons, is really lopsided with respect to its electrons. So this molecule would get this type of designation and funky symbols. This symbol means partially positive charge. It means that side of the molecule is like the positive side, the positive pole of the battery. And this side of the molecule is negatively charged. Sometimes. They're not ionic. It's just that that side of the molecule pulls the electrons to it over the other side. So it creates this kind of like magnetic north and south pole kind of thing in the molecule. And that's why we call it a polar molecule. Now H2O, we would look at. Let's do H2O. We'll put the oxygen in the center. because that is the most electropositive element. It will have 2 pairs of electrons lone hanging off of it. It's going to have 2 covalent bonds coming out, and the hydrogens are going to be on the ends of those covalent bonds. So we've got 2 lone pairs of electrons. And you can see here that we're definitely not going to pass the mirror test. If we cut the molecule along the x-axis, you can see the top and bottom are not the same. And even furthermore, if we cut it along the y-axis, you can see the left and the right are not the same. So this is a polar molecule, not symmetrical. Not symmetrical means polar. Okay, so let's move on to a couple more examples here. Nonpolar molecules are the opposite side of the story. We have symmetrical shapes with equal sharing of the electrons. That does pass the mirror test. They can be folded in on to reflect itself, and it's when 2 atoms have the same or almost same electronegativities. And more than 2 atoms, well, we've got no unbonded or lone pairs of electrons around the central atom. Here we go. Cl2. Well, there's not really going to be a central atom here because we have to put a Cl on one side and a Cl on the other side, connected by that covalent bond. Now, all the chlorines, after we've done our Lewis dot diagrams for covalent compounds, we'll see that each chlorine here has 3 pairs of unbonded electrons. And we're looking at the symmetry test. If I cut it down the middle, left-hand side matches the right-hand side. And if I cut it across the center on the x-axis, the top-hand side matches the bottom-hand side. So this is a very symmetrical molecule, and that equals non-polar. There is no side of this molecule that's going to attract electrons more than the other. Okay, that's our only example there. So a couple other molecules, CO2. Now C, carbon, is going to go in the middle. Oxygen is going to go on either side. I'm doing this because I know my Lewis dot structures for covalent compounds very well. We got double bonds happening there, and then we have lone pairs of electrons on each of the oxygens. That's CO2. Let's see if it passes the mirror test. Cut it down the middle, left, right, matches. Cut it down the center, top, bottom matches. So this is a non-polar molecule. Now CCl4. We put carbon in the middle because it's the most electropositive, least electronegative element. And put carbon in the middle, central. We'll put the chlorines around the outsides. We'll put in our covalent bonds, showing the shared pair of electrons between those nonmetals. And we'll fill up all the lone pairs of electrons on chlorine. There's a lot of them this time around because there's lots of chlorines. Keepers. Then we have to see if it passes the mirror test. All right, do we pass the mirror test? That looks very symmetrical to me, so I am going to call that non-polar. Absolutely. So beware, there are often polar bonds inside nonpolar molecules. Look at these 2 examples. If you wanted to see if you were ignoring, if we're ignoring the other 3 chlorines in this example, and carbon tetrachloride there, if we were to just look at this scenario, you could see that the electrons are getting pulled towards chlorine because it's more electronegative. But since there are other chlorines balancing out the one that we have there, the whole molecule is, in fact, symmetrical. So even though the bond within the molecule might be polar, the entire molecule itself is nonpolar. So at this point, you should have a basic understanding of how to look for molecular symmetry and how to compare the elements' electronegativities in order to maybe see which direction the electrons are being pulled in. So we're going to have a little bit of practice in class about that. It's page 37 to 39. And I hope that you understand a little bit of symmetry here. So thanks. Have a nice day.